Good to see you here, Priya. Good to see you here, John. Can we go over to What's Right for Visualization 3? And can we do some 2F on assignment 3 for BAS 320? Yeah, let's take a look at all that. I'm going to get some screens going here. John, great question. John's got the BAS, and great to see you here, Priya. And let's go live chat. Say hey if you're in the chat. Let's wake up Mubot. I think we're streaming. There was a time where I streamed to a class. I was talking, everyone's like, when's class gonna start? And I was like, we're here right now. We're saying hey. And then everyone's like, when's Brian gonna appear? And then I was like, oh wait. I never started the stream. So yep, it says we're live. I know what to look for now. Assignment 2F. Assignment 3. Question 2F. Stat tool 1. Visualization 3. Writing. Write-ups. Helping with interpretations. Okay, we got the stuff ready to go. Jump in the chat. Say hey. We got everyone here, it looks like. Let me pull up the assignment. And we're wondering about 2F. 2F. I love it when it doesn't say what the question is. Let's go grab the questions themselves. Okay. Gotta go find the book. We need a little chill music right here. Where's that chill music at? That's nice and chill. Love it. And let's head over to the main screen with the BAS 320. We're getting the book open right now. And here we are. Where is the homework packet? There we go. Okay, so 2F. And John, feel free to follow along. I'm going to ask lots of questions right here. I think we're streaming. I think people can hear me. Might be wrong. Not the first time in my life. So here we are with the book. Let's check it out. So the homework packet is located online under the modules. Time stamping this right now about 5 seconds ago. 2, 4 to 3. Doing some assignment 3, Q2F. Can we go over 3B? Oh, sure, of course. Got that over here. James, great to see you here. Assignment 3, question 3B. I got it listed. It is 2 away. Good stuff. Oh, we're right on 2F right here. I think this is 2F, right? Okay. The discrepancy between all expected and observed counts turns out to be 1.017. Below is a simulated sampling distribution of the discrepancy, that's what D stands for 5,000 samples with no association. If the association between location and gender is so significant, why or why not? Is it? Okay. So here's the thing. We need to know what a discrepancy is. A discrepancy is basically, in this instance, what we are seeing. We have it open from earlier. Right here. Got the hiccups. We have a discrepancy of this red line right there. We have a discrepancy over here. Who knows what kind of graphic this is for 100 points? Who knows what kind of graphic this is? We have a discrepancy in these top graphics. What are those top graphics called? So this is a visualization of a large discrepancy and a small discrepancies in what plots? What are these graphics called? 201's like, hey, I've seen those before. So we have examples, which actually I think 201's doing this for their assignment. Sorry about that. Let's go on. There we go. Now there we go. So what are these graphics called? What are these graphics called right here? These graphics are called mosaic plots. Great job right there, James. They're mosaic plots. And a mosaic plot is going to be a categorical relationship. When you see a big discrepancy, there's difference in the conditional distributions, which is what 201 is going to be interpreting, where there's small discrepancies over here. Discrepancies are not limited to mosaic plots, though. They're also in side-by-side box plots, which 201 is also doing right now. You can see very large discrepancies, which are seen in differences in the medians. Oh my gosh, I'm not speaking well today. Between the box plots, where there's small discrepancies over here in example section 2. So when we find the discrepancy, we can actually get the numeric value of it. And the numeric value of the discrepancy has to be found via R, and it's the sum of the cell chi-squareds. We do not need to find this, though. Let's take a look at a data set right here and just look at some discrepancies in Survey 9. So let me go here to attach Survey 9. We're going to look at some discrepancies. And there's the Pepsi data we were working with, survey 9. Let's go look at, is there a satisfied with weight? I don't have that many snooze on. Oh, H1N1, that was interesting. Do you use chopsticks? Your views on Obama? All these different things. Business major. Oh, interesting. Frequently dropped calls. Married at. Scholarship where you sit in class. You go to church. Cool. So we got here X02, gender. And we have X09, do you go to church? And then Y tilde X comma data equals, and survey 9. Now it says figures are too large. We got to increase that right here. We're seeing that there's an association between someone's gender and do they go to church. And what do you notice right here? Actually, there is somewhat of a difference right here. That is the discrepancy right there visually. And females in the data set were more likely to go to church. And I have my significant digits or my round. We go to option, digits equals 7, and SciPen. That sets the scientific notation to 7 and the significant digits to 7. So we see a little bit of a difference right here. And you can see for the females on the conditional, given someone was female, they went to church, or 42% about went to church compared to the males. The difference right here is about a difference of 10%, which is a bit of a difference. That's a bit of a discrepancy. But we get into the bottom right here where we are looking at what our question started us off with. And let's bring up the graphic the question shows and think about what's being calculated right here. These are random permutations, as though the data has no relationship. And the smallest discrepancy possible would be 0 when the plot perfectly matches up. So what do we see in this example, which is another example? We see once again the smallest discrepancy of 0, but we see our discrepancy is at 5.56 right here. That's where 5.56 is at. But remember, all of these discrepancies are created by random chance. So if I were to redo the graphic changes. And it's even more apparent when I say only run it with permutations equal to 10. So now here's the 10 random permutations that are created. And every once in a while with 10 random permutations, we might see that one of the permutations is beyond our discrepancy. This is very important. Since one permutation is beyond our discrepancy, what would the p-value be? Who knows in the chat for 100 points? Since 1 out of the 10 was at or beyond our discrepancy, what would the p-value be? Since 1 out of the 10 random discrepancies, so we had a discrepancy of 5.56, and I had 10 random discrepancies right here, 1 out of the 10 of the random discrepancies we created was at or beyond ours. What would the p-value be if 1 out of 10 was at or beyond ours? Usually we do, so for this, ours are right here, but in 201 it'll be the row percentage. You're in 320, right, James? Ours are right here. The marginals are right here. And if we have it in a table, this would be, excuse me, not marginal. I think you said it properly, actually. Yes, right there, 100 points, James, you said it properly. James is saying this, I misspoke, my brain broke. This is the marginal distribution of whether somebody goes to church. This is the marginal distribution. Let me highlight it and draw it. So we're looking at the marginal distributions here. And let me highlight it. And the marginal distributions are going to be this. And the marginal distribution is going to be here. So there's the two marginals. They just share the total. So does that make sense right there, James? To your question, the marginal distributions are the distribution in the margin. They only show one variable. I was thinking conditional for a moment. My brain was just on conditional as we talk about given someone is female, given someone is male. And you do actually get a marginal distribution down here, which is for everybody. So this would be the percent of everybody who does not go to church and the percent of everybody who does go to church. This is the conditional for going to church. Notice how the marginal is over here on the margin, and that's the marginal for everybody. So this is the marginal distribution of people go to church. This is the people who do go, 37%. These people who don't go. And then we see for males only, which you see fewer amount of males, 32%, and for females, 42-ish%, basically. And that's the conditional given someone is female. And make sure to read the output. It'll usually walk you through it saying conditional distributions and marginal to make sure we have good words to use to describe this. With this right here, think about this, James. Only 1 out of the 10 random permutations were at or beyond. So our p-value is what? 100 points, James, for following along here too. our p-value would be what? Because only 1 out of the 10 random permutations were at or beyond where we landed. We landed right here. That's where our discrepancy is. So what would the p-value be? If 1 out of 10, only 1 out of the 10, there's 10 discrepancies, like it'd be 0.1. Exactly, John. Great job right there. More points in the chat. So what does it mean when it says the p-value here is 0.3? What does that mean? There were what? And you can kind of see them right there. Luckily, we can still see it pretty clearly. There were what random discrepancies that were at or beyond ours? Like, how would you interpret this? This being 0.03 with the 100, this would tell you the percent right here, but you can see them 1, 2, 3. What does that mean? Out of the 100 random discrepancies that we created, the ones that were at or beyond ours were 3. So 3 out of 100 random discrepancies. So what about if I do something crazy like this and we don't interpret it as how many, but we just interpret the p-value as a what? The amount of random results that were at or beyond ours was 0.0165. So now we have a much bigger graphic with more discrepancies. But the amount of random discrepancies, so you might not even see it now, but the amount of random discrepancies was 1.65%. 1.65% of random discrepancies were at or beyond our discrepancy. Does that make sense, John? 1.65% of random discrepancies, because these are all random, were at or beyond our discrepancy. We can bring it back to a smaller example to where we can see none of them are beyond. And once again, every time we do it, it's random. And there's 1 beyond. We might actually get 2 at some point. Oh, that was 2. It was. I should go back. See 0, 0, 0, 0, 1. We'll never get 2 again. Never. Really? That's unlikely. Very unlikely. We saw it one time. 5, 4, 3, 2, 1. Well, we can't spend the rest of the time doing that. That's a bummer. But the thing is, we wouldn't do it that way. We'd just increase the permutations to get a better estimate. It runs by default with 500. So now we would say 1.8% of the random discrepancies were at or beyond ours. So let's think about how this applies to our problem. Our discrepancy was at 1.017. What do you think if we were drawing an image of this, would we put right here? This is not a bad thing to add to your assignment. By screenshotting here, and you could add this into the Word document later. What should I put at 1.017? What would I draw at 1.017? Who knows what I would add to this graphic to make it look like the other one at 1.017? And this is what it does for us. What would I add to my graphic at 1.107? To like start making it look like the other graphic to find a red line. Exactly. And the p-value is the percent of area where? Where is the p-value? The p-value would be the discrepancies that are what? The p-value would be the discrepancies that are what to my discrepancy? Because it's the probability of results like our result or more extreme by random chance, given that there is no association. The p-value for this would be the what? Like if you calculate the p-value here, for which this is very small over here, then our p-value would be where on this? Like how mathematically, where is it? Exactly, James. It's going to be the area at or beyond. So you can see we put them both on the screen right here. This is a very small p-value due to a large discrepancy. And here we're going to have a very what p-value due to a what discrepancy. So here, and this is good theory for the test, here we have a what discrepancy leading to a what p-value. Generally speaking, this discrepancy is very what leading to a what p-value compared to the other one, especially. This discrepancy is very what leading to a whatter p-value. This discrepancy is a lot whatter. Put some 100 points in the chat. Large p-value from a small discrepancy. So that means the differences we are observing with what we did with this example over here is likely due to random chance. Like there really is no association between someone's gender and where they sit in class. Any sort of discrepancies we see are rather small and probably due to random chance. Does that make sense, John? The discrepancies between people's genders and where they sit in the class are rather small and probably by random chance. When I say probably by random chance, I'm talking about the p-value here telling me maybe this p-value is what? It's the percent of area we've shaded on this curve. Well, the whole curve is 100%. but we've shaded here maybe like 80% of the curve, which would lead to a 0.80 p-value. Now, that's just an estimate, but this is definitely greater than what? Like that shaded area is greater than what number, which is very important for p-values. It's definitely more than this percent of the curve. So our p-value is definitely more than this, which would tell us it's not statistically significant. For certain, I know that that shaded amount of curve is more than 1. It's more than this percent of the curve for certain. Like someone's like, here's a slice of pizza, and I say, I'm taking this much. You're getting the crust. So you think about the crust of the pizza is only... I'm taking all the good parts of the pizza. Maybe they want the crust. But I would say that p-value is definitely more than 5%. And that's when we reject the null. So the p-value is way larger than 5%, which would indicate to us it is not statistically significant. Hey, what's up, Troy? Ask questions. We got a few on the docket, but let me know right here. And so is the association statistically significant? No way. No way. The discrepancy is rather small, indicating there is a large p-value, and the results we see are likely due to random chance because there's a lot of permutations that are at or beyond ours. Good questions right here. We're going to hop to the next question. Troy, great to see you. Troy, 100 points in the chat. Thank you for being here, Troy. Drop those questions in the chat. Let's do this. Next question is some visualization help. Let's go grab the Stats 1 visualization help. Okay. I'm going to drop a video. Number one skill to have is being able to interpret and communicate results in data. So we want to have these skills where we can interpret and explain data to people. So, oh, there I am right there on the screen. Let me find something. Okay. Here we go. Actually, I'm feeling really good about all the chapter 5. Oh, great job. Yeah, Troy, thank you so much. Felt bad that I answered the door because the telephone guy came by, but we need to get our telephone fixed. So the joys of working from home. Troy, great job and great practice. Let's go check out the visualization. Here we go. So if you take a look right here, I have up right now video from, I think it was Monday. So I'm still going to go over some of the visualization. Do not worry. Some of the visualization right here. Let's go grab this. It's time-stamped right here. Copy at current time. Check out this video. It's time-stamped at the current time that I'm at. You'll hear me talk about it, give advice as we work through it. You will see me go through its timestamp with the mosaic plot, timestamps with the box plots, walking through. So we're going to add a little bit extra kind of ideas to it right here. I don't know what's going on with my hair. I'm going to cut it soon anyways. Hair is getting crazy. So right here, just overlapping Brian's right there. So with this right here, check out the visualization playlist, or not the playlist. Well, you can do the playlist too, but hop into Monday's video and see as we explain it. And that's kind of what we're talking about here. Should we talk about which one are people wondering about the most? The box plot or the mosaic plot? The box plot or the mosaic plot? Which one are people wondering about the most right here? Box plots or mosaic plots? Because as you can tell, with box plots, we have certain measures to compare. With mosaic plots, we have other things to compare. So mosaic plots, let's do the mosaic. So the mosaic is right here, but we're going to hop into our own example today. So if you're looking for a step-by-step, check out that link I just dropped in the chat. So I'm going to make one right here, not so much step-by-step, but let's interpret a mosaic plot. Here we go. So we need the instructions up first. Make sure to follow along with taking your random sample along with analyzing the variables it asks you to analyze. You'll need to make sure you only have the total and the column percentages. And I always want to say, because I don't know which videos, I want to say this in each video, that I don't know which videos you watch, make sure to check out you follow these steps. Look at the instructions, follow what it says, make sure you complete each and everything so that you get all the points. Like include your name, take a random sample, and follow along with everything here where it says the full marks. Like don't do these. These are the ones you lose points on. So be over here where you follow the instructions and do this right here. Terry and everyone's done a great job of being very clear in what you need to do. Let's take a look at jump. I'm going to load up some jump right here. So 2 seconds. Load up jump right here, get the jump data loaded up, and we're going to make a mosaic plot. So what kind of data does a mosaic plot take? Sometimes our questions are as simple as that. What kind of data does a mosaic plot take? A mosaic plot is a visualization of this kind of data. Who knows in the chat? Mosaic plots visualize what? What would a mosaic plot visualize? It's always this variable. I'll help us out right here with our mosaic plot investigation. Bivariate, I like that right there for 100 points. Bivariate and bivariate categorical. Great job, Priya, right there. Bivariate categorical. Exactly. So you have your own variables you'll be analyzing. Make sure to look at those. Let's take a look at somebody's smoking habit. And let's see if somebody's gender explains their smoking habit. Smoking habit's a bit longer of a variable. I'm going to do something really quick. You wouldn't normally have to do this, but I'm going to make my life easier. Where's smoking habit? Here it is. I'm doing something to help myself out. No multiple smoke. Oh, I wish we collected data on this over the years to see how vaping has changed. Other. Okay. Makes life easier. Let's go to gender. And does that explain somebody's, where is it at? Smoking habit, 2. Okay. Just first off, what do you notice? So there we have male, we have female. What's the first thing you notice? I see it right here especially. What is some things you notice immediately that just the mosaic plot communicates to you about males or females? What do you notice? Just the first off thing with the mosaic plot is we have 2 categorical variables. We have whether someone answered male, whether someone answered female, and what their smoking habit are. The cells are different size. We see what we call in 320 discrepancies. Like there's discrepancies here. Ooh. Talk to me about this green thing. What's going on with that green thing right there? What's going on? Talk to me about what this green thing is right here. Maybe it's like, oh, don't do that jump. Maybe this green thing right here is 65%. And then this one over here is 84%. What's the deal with the green thing? As Jerry Seinfeld once said, I don't know why he said that, but he did. So what is the deal with it? What is it? What does it mean to us? 65% of who, what? 85%. That's basically 85. I'd write the decimals. I'd write 84.7 if I'm going to write it down. But if I'm going to talk about it, I might say about 85 and 65 comparatively. 65.07 if I'm going to write it. I'd carry decimals while writing things. These are what's. I'm comparing what's. What do you notice right there? And that's kind of a key one for this. That's pretty interesting. Pretty big difference. What do you notice? What does this mean to us? And then we'll find it down there in the contingency table here in a moment. But what does this mean to us? That's what of the who. Then we're kind of good answers out there, 100 points. Not really the number of people, but the percent. This is so when we look within only the males, this is called a conditional distribution. So this is given somebody is male, the probability that they did not smoke. Given somebody is female, the probability that they did not smoke. Now this is all people smoking or not smoking. That's the marginal. So what we want to do is we want to make our contingency table look like this by going here and removing total and removing column percentage. I'm also going to take and do a trick. You can screenshot both if you want. I'm going to click this right here and now drag and drop. And you have to wait till a long bar appears right there. Now this gives you a side-by-side view of it. You could screenshot this. I'm going to click back here to this and click away from this. Control click removes it. But now I like this view of it. And we'll try to make it look nice and neat right here. But there's a good graphical screenshot of what we might want to try to communicate to somebody. So let's go ahead and screenshot this right here. There we go with this. And here is what we could put in our visualization assignment. So when you look at this, what do you notice? Here's the counts of individuals. But females were way more likely than males. And you could mention the percentages. You need to mention percentages. Females were what more likely than males to what? So we're looking at the smoking habits of males and females. Females were way more likely than males to what? Vaping is one of the closer categories. Females were way more likely than males to what? Like if you think there's an 84% probability versus a 65% probability, when you compare the females to the males, they were way more likely to not smoke. We have here 84.7% of females. Exactly, Troy. Great work. 84.7%. And these are called conditional distributions. This is the conditional distribution of males smoking and not smoking, rather. Or, well, the full thing is the conditional distribution of what males do. And that would be the percent of males who don't smoke versus the conditional distribution of females and looking at the percent of females who don't smoke. So given someone is female, the probability they don't smoke is 84.7%. Given someone is male, the probability they don't smoke is 65.07%. So there's a big difference right there. That is indication of a pretty strong association that somebody's smoking habit is probably highly associated with somebody's gender to a certain extent. Doesn't mean you do smoke. Think about this. Most people don't smoke, but males would be more likely to use things like vape, smoke, other or multiple products. But still, 2/3 of males, just about 2/3, don't smoke. So you can't say, oh, you're male, you smoke. No, it's just if someone is male, they're probably more likely to smoke. Doesn't mean they will. And actually, they are more likely to not smoke, but they're more likely than females to smoke. So that's what we mean by an association. That if you knew somebody's gender, it might give you an idea or narrow down possibilities. Once again, don't assume, because in truth, you should realize that most males don't smoke. So you'd actually be right to just predict, oh, you don't smoke if you're male. But you'd say you are more likely to smoke if you're male, though. I wouldn't be shocked. I don't smoke. So at this right here, these are the conditional distributions within here. Like everything within here is the condition on somebody being male. Like all those numbers is conditional on male. And all these numbers here are conditional on being female. And that relates to these right here with these numbers right here. These are the conditional distributions right here for female, as you can see, respectively, and for male. Give me back my normal stuff right there. Hey, you, give me back my gold symbols. And so there we go right there. There's the marginal on the side. The marginal down here doesn't show the percentages, but it has it right there. Priya, what do you think? What additional questions do you have? Let me know. Is this making sense right here? We need to start doing comparisons and talking about, do we see differences? I'd say a nearly 20% difference. And if I'm doing this for the project, I'm going to pull out my calculator. And I'm going to say the difference between the percent of females who smoke and the percent of males who smoke is, I'm going to write this down. I'm going to say, I'm going to say 19.63%. There's a 19.63% difference between females and males in the percent that smoke, with 84.7% of females not smoking and 65.07% of males not smoking, which also would indicate to you that, around 35% of males smoke to some extent, and around 15.3% of females smoke to some extent. So then I'd start talking about, like, one of the big differences we see is that around 1% of females. That's so weird. Just cigarettes. I remember when I was in, like, oh God, it makes me sound old. I walk out of class and, like, people would just be standing outside smoking cigarettes. Maybe it's not socially acceptable to say that you smoke. Like, people smoke, but they just don't say it. Be interesting. Here's some response bias on the survey. So I don't know. Maybe there's response bias in this. I don't know. What other questions do you have? We'll probably jump back to some 320, but make sure to check out the video from earlier this week. But let me know if you have additional questions. The main goal of talking about a mosaic plot here is to compare the conditional distributions. So we have to talk about all the numbers, just like I would think about how to make comparisons. It doesn't hurt to write a little extra. Talk about, do you think there's differences or do you not think there's differences? In many instances, there might not be differences. Hint, hint, hint. Like sizable differences. Like if I look at something right here, like gender and probably like family economic level. There's little bits of differences there. Much smaller. Wait, is this the one we're doing? No. We're doing family order? No, we're doing broken bone and family order. Yeah, broken bone and family order. Looks similar. It actually looks very similar. Hint, looks very similar. The differences here look smaller and more likely by random chance. Ooh, actually not a little bit. Hence I looked at it and I was like, let me get a worse one. well, smaller differences. How far someone is from campus, and if they've broken a bone. Yeah, here we go. That's what I wanted to see. This one right here, how far someone is from campus, and this is not the one on the box. Here, we'll take a look at it here in a second. Yep. So this one has very small differences, which are likely by random chance, which indicate independence. Does that make sense right there, Priya? We need to compare the differences here between people who have broken a bone, similar to your problem, but not quite. Very long table, which I don't love working with. But we need to compare these percentages. And you notice the differences here are a lot smaller, between like 34 to 30. It's actually one of the biggest differences. 23.9 to 24.8. Comparatively to the other one we just did, where the differences were like 85 to 65% comparatively, or 1 to 5%, or 12 to 18. There's much bigger differences here, which gives stronger evidence of an association. Like knowing someone is male would give you a stronger indication that they smoke. Doesn't mean they smoke, just it's more likely that a male would smoke. That's what an association is. Where over here, knowing someone has broken a bone really wouldn't be that associated, i.e. it would be independent. So I would say this is more independent, where the other graphic we did is more not independent. This is an example of not independent, and this is a good example here of probably pretty independent. So independent and not independent right here. And p-values also tell us that too, but we're not talking about p-values right now. When it comes to side-by-side box plots, with the side-by-side box plots, which variable on these side-by-side box plots should be your y variable? So when it comes to side-by-side box plots are a visualization of a what and what variable type. Take a moment, 100 points in the chat. What kind of variables? You might go away. What kind of variables are side-by-side box plots visualizing for us? Take a moment. And so what variables will side-by-side box plots be visualizing? Yeah, that wouldn't be practically correct. Small differences are not that practically significant. Correct. Good job right there, Priya. Good answers. And make sure to talk about the differences you see in the conditionals. Side-by-side box plots are what kind of visualization? So connect the things right here. Side-by-side box plots are what visualization? Well, it's bivariate, right? And so with side-by-side box plots, we would have a And so the categorical is the what variable. Look over there. Just type one letter in the chat. Look over there where the categorical is at. The categorical is the what. So use this to decipher it. The categorical variable would be the what variable. In side-by-side box plots, the categorical variable would be the what. Because box plots have a quantitative y. So if you see up there at the top of the screen, the box plots have a quantitative y. Correct. And then we're going to break it apart different categories with the x variable. So that's what we have going on right there. Let's go back and check it out. So if you can tell right here, we have born in Tennessee, which is categorical, and high school GPA, which is quantitative. So when you're over here in Graph Builder, you want to go to Graph Builder, and then you'll take the quantitative y variable, and then you will split it up right here. And then you'll click the box plot button. Remember, we do go through this in the earlier videos. And you do want to also click the 5-number summary. Let's make it bigger. 5-number summary. There we go. Got some overlap on stuff. Not really much differences. Now you want to check out the earlier video where we compare the medians, we compare the IQRs, we talk about some values. But you want something like this right here. So you see the X variable breaks it apart into groups, categories, puts the box plots side by side. The reason you don't see the median is because it overlaps. So we have right here the min, and notice right there, the min is an outlier. There's a lot of outliers here, but these are side-by-side box plots. Priya, does that look good? What are you thinking? Do check out, we put the video earlier in the chat, but make sure if you have any questions, let us know. Practicing the visualizations right here. Kind of a quick overview. We need to start comparing metrics here, but good stuff. There we go. For chapter 5, homework part 2, I'm stuck on the one where, oh, yes. I think you just found my favorite question, Summer. That makes my day. We have one more question, and then we'll be doing that next. Stat 201, Chapter 5, Part 2, areas under normal curve. That is one of my favorite ones. Would you say that a difference of 5% is not a difference? is it sounds small. It sounds smaller. Give your thoughts, whether it's a large or small or kind of small. You can use describe. You can use like kind of small, very large, huge, ridiculous, tiny, non-existent. So think about how. I mean, it is a difference. Is it small? Is it kind of small? Is it large? Is it medium? So think about what it means and how big of a difference it is. Like I would say here that these are very large differences when we see 84 to 65%. That's pretty large differences. Over here, the differences I observe of a difference of about 5% there comparatively with the different groups. The 2% difference here and the 1% difference here is not that large. Like these are rather small differences. They're not non-existent, but they are small differences, likely due to random chance. We don't talk about p-values yet, though. But these are rather small differences. A cheat is to see your p-value. If it's big, then the differences are probably due to random chance. But we're not talking about p-values. Don't talk about p-values. But the other one had a very small p-value, which indicates large differences. And check out earlier in the video, we were doing that in 320. So you'll see us talking about p-values and discrepancies in mosaic plots with 320's way of talking about it. Yeah, 3A, you bet. Do we have that on the list yet? We got 3B. Do you want to? I think, John, you asked about 3B. So let's do 3A and 3B, John. Here we go. Back to the main screen. John and everyone, big shout out. Thank you for being here. You're welcome, Priya, and thank you for all those questions. Thank you. We're the number one thing to do, and I really appreciate it, is everyone who's here interacting, and people watch the videos later. You're awesome too. But the number one way to learn things is to be here, to interact, and just ask the questions. It's different if you're watching it later. So it's a little different. So John, your call, you're here. We did 3A and 3B last office hours. So if you want, we could do C and D. But your call, John, do you want your call? Don't feel pressured. We could do C and D right now because you're the one who's here. And there is 3A and 3B in the earlier office hours. I'll show you where they're at. We did 3A and 3B at the start of last office hours, so we can do them right now. And I'll do it differently, so that way there's a little bit different of learning on it. So there, it's at the start over there. What would you like, John? Would you like to do 3A and 3B, or we could do 3C and D? Your call. You get to pick. So I'm always trying to do like different things in the videos, but your call, you are here, you get to pick. If you're like, I'd like to go over this with you, we got it. If you're like, I'll check those out later, and if you want to put C and D in this video, your call. John decides everything. We got this. Let me know your thoughts. Can we do 5 now? Of course. So then we'll do 5. Yep. We can jump to whatever one you want. Okay. Is it the government conducts the census? What does 5 say? I think 5's like a different question because it's like exercise 6. That's confusing. Okay. Let's go check it out here. Let me go get the timestamp. And then we got area under the normal curve. Not joking. One of my favorite questions. I love it. And you'll find out why coming up here soon. So let's go do areas under the normal. Let's go do assignment 3, question 5 for BS 320. Let's do this. Okay. This is question 5, but it is from example 6. Use EX2 tips. This data set records the bill and tips amounts along with the tip percentages as well as the party size of people who were at the table and whether they smoked. We're still just talking about smoking today. Now, the thing about EX2 tips is it's inside of the reg class package. So the reg class package is something you'll need to have loaded up. Here it is right here. Boom. Now that works because I've already loaded the library reg class. If this does not complete for you, make sure to install reg class. Reg class is the regression class package, and it is on the CRAN server. A lot of info you don't need to know. Just make sure you have it running, and run it by running reg class. And if you don't have it installed, make sure to do install.packages, autocomplete, quote, reg class. It has to search for that string. Make sure to install it. And you know what I'm even going to do? I'm going to put this in the chat right here. Copy this out of the chat. Make sure to install it and then run it. Don't leave the installs in your knitted documents. It'll crash your document. Lots of errors can occur. Lots of errors. So use the associate command, okay, and use the suppress warnings to suppress warnings. Cool. And we want to use seed 2020. Cool, fun stuff. Okay, where's the thing? Oh, wrong thing. There we go. I have it over here. Why did I put it? Well, I guess sure why. Okay. We are curious whether there is an association between the size of a party and whether they smoke. Party sizes range from 1 to 6, so in this case, it is appropriate to compare the average size between them when using the averages. That's all it says. Run associate to perform this test using the default number of permutations. Why is this test inconclusive? Now, there is something I do want to mention right here. It is possible, and I think that's why we're using Seed 2020, to get conclusive results. But let's talk about what an inconclusive interval means. So let's run this test, and then let's talk about that. That's not a new sentence. Oh, cool. Well, let's just grab this code. Grab code. So that's 6. So are you talking about this one right here, John? Are you talking about this one? Or are you wondering about 6B? Are you wondering about 5? Like, which one are you? Sorry, John. I'll make sure we're doing the right one. Are you wondering about... Are you wondering about question 5, exercise 6? Or... Because it's a little bit confusing on the numbers, right? Which one are you wondering about? Yeah. No. It doesn't help that it goes a little bit out of order, right? It's a little bit confusing. So with this right here, the associate function allows us to look at the association between two variables. So when we look at the EX tips data frame, it's going to be over here. Let's take a look at it. Oh, yeah, I know, right? So, yeah, sorry. Hopefully that doesn't have anyone make a mistake. It could be easy to make that mistake on it. Very easy. So let's go to the association between size of party and tilde smoker data equals. Now, John, do you know the format we use to make these models to large figure? Do you know the format we use to write this equation? So there's a very famous format with the associate function or many other functions called y something something. We already saw it today in BS 475. If you are already using it, what is the format we use? What is the format we use? What is the format we use? Do you know it? If you don't, that's all right. You'll hear it a lot for the remainder of the semester. The format we use is, for 100 points, who knows? Like someone jumps in from like 475 for some further, oh my gosh, y tilde blah, 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 blah. So the format we always use is y tilde x, comma, data equals. So that's the format we will always use. You'll see a lot of this is the y variable of interest. This is the x variable of interest. And then the data is the data name right there. So y tilde x, comma, data equals. The suppress warnings just removes warnings if warnings occur. Warnings are just like, hey, did you know this happened? Like it's mad about my graphics. That's not a warning. That's saying I can't do it. Because the, it's mad about an in-graphic figure state? What? Might need to reset R. It's just going to be totally mad today. Let's reset R right here. Reset R. Reboot R. And that should actually fix the issue a lot of times. You'll be shocked at sometimes just turning on R on off. Turning R on and off fixes the problem. Did it fix the problem? Did we lose our code? No way. All right. Well, we lost our code. Library red class. That's why you save your code. Oh my gosh. There we go. Load that up. And we want to go here. I'm going to do a trick. Attach ex2 tips. Technically, this code should go after it. That's going to attach it. And then let's go here. We'll first get run. Size of party. Smoker. Since I attached it, I now have autocomplete options. And then ex2 tips. And then it runs. Literally turning on and off R will fix problems sometimes. The invalid graphic states, I think because I was working with ggplot. ggplot kind of had made some stuff that didn't want to work with these graphics. So I just reset my R without ggplot running, and now the two things aren't interfering with each other. You probably won't run into that issue. It's just because in time series today, we were doing some pretty neat graphics with ggplot and probably was creating that issue, probably. Now, if you don't run the suppress warnings, which what I was going to mention, is you will get warnings saying like, no, we don't get warnings? Oh, we don't. So it's unnecessary for this one. Sometimes you do. Suppress warnings just makes it so you don't see warnings. It's just wrapping your code in it that the output won't have warnings. You can suppress messages, you can suppress warnings. It just makes it so those things don't occur. You can suppress package startup messages. Oh, that's cool. I guess for libraries? Didn't know that. Suppress foreign check. I don't even know what that does. So that just makes those things not happen. If there's a warning, it won't appear. So here's the big thing, John. We need to know how to interpret this output. And this is where we'll be getting to in class today. We'll still make the output. Good, we're good. Can I get it all on one screen? Good. It asks, why is this test inconclusive? And we need to use the seed. John, do you know why this test is inconclusive? So pretty simple question. Why is this test inconclusive? Well, there's two big things to talk about right here. One, what is the p-value? So John, for the test of the means, what is the p-value? And this is the easy question. Let's put some notes here on the screen. The easy question right now is, what is the p-value? So let's talk about statistical significance. You have to do the attach. So you have to do attach right here, and I do that below, and that'll give you autocomplete options. What it does is it attaches the vectors to the global environment, so that way you can autocomplete without using the data set, so you don't have to be within the data set. So attach puts your vectors to be aliased or connected to the global environment, so it attaches them at the base level. So that way you're not having to do the $ to get to them. Some people don't like it. I like it. I like autocomplete. You would need to load the data, then attach the data. Make sure to try knitting your document, because if you put things out of order, things will crash. So attaches them at the global environment, so then you have the autocomplete options. It really helps with things that might be capitalized or have underscores, so that way you can just go down here and type something like size, and you can get the autocomplete right there. If it's not attached, you can't do it. So if I go here and detach it, it won't be available anymore. And now I go and type size, and I don't get size of party. So attach attaches vectors to the global environment, making it available so you can autocomplete with them. Neat little trick, makes things easier. Yeah, John, great work. Good questions. Ask those questions. If this doesn't work, that doesn't work. Little function like that will change things, and that's why we utilize little functions to be like, oh, let me just make it so I can get some autocomplete. So attach I just use to get my autocomplete options, so I don't make typos. With this right here, what is statistical significance? Review from last class. What is statistical significance? What is statistical significance? Now, we do see multiple things related to statistical significance on the screen. What is statistical significance? I say statistical significance. You say this. So if I'm ever talking about statistical significance, you'd be like, oh, he's just talking about the what, and if it's below this value. So he's breaking into a New York accent. He's talking about the this, and it's below this value. So statistical significance is always the evaluation of what, and it's below what value. So whenever we say statistical significance, we need to be like, well, what's what? Bingo. P-value less than 0.05, not save into. P-value less than 0.05. This is only answered with yes or no. If it's at 0.5, it's not below 0.05. This is answered with yes and no. But then we have a second question. Conclusive on significance. Conclusive or inconclusive on significance. Okay, so what does it mean to be conclusive or inconclusive? And I'll not show the p-values on this. To be conclusive or inconclusive, we would probably need to be confident and make confidence intervals. So when we talk about whether it is inconclusive, p-value in the interval, inconclusive, or excuse me, 0.05, not p-value, no, 0.05 in the interval, it is inconclusive. 0.05 not in, then it is conclusive. So it is inconclusive when 0.05 is in the interval. Why is that test, which is pretty much the answer up there, why is that test, why is this test right here, why is it inconclusive? Why is the test of the mean inconclusive? Inconclusive. Why is the test of the mean inconclusive? This one's also inconclusive. This one is conclusive. Like it comes to a conclusion. Like we're like, that's not significant, and I'm sure of it. 0.05 is in the interval. So the test is inconclusive when it has 0.05 in the interval, because we're like, I don't know. Think about this p-value, and look at it this way. 0.02, is that significant? Yes or no? By 0.05 standard, is that significant? Yes or no, John? Is the p-value 0.02 significant? Yes or no? You can type Y or N in the chat. Is 0.02 significant? What are your thoughts? Is 0.02 significant? 0.02? Yes. But what about 0.05? Is 0.054, excuse me, is 0.05 still? Is 0.054 significant? This is why it'll be inconclusive. So this was significant, and 0.054 is it significant? Is 0.054 significant? No. So look at this. You go from thinking maybe it's significant to maybe it's not. You're inconclusive. This one is, a lot of people get this wrong. This is conclusive because it's not significant, not significant. Conclusive means that it doesn't go through 0.05. A lot of people think that one's inconclusive because it's not significant. Significant just means below 0.05. This is not significant, but the interval is conclusive. Does that make sense, John? If I say like, this test was not significant, but the interval was conclusive on that result. So whatever you decide up here, is your decision conclusive, will be if 0.05 is in the range. So very important to know that. Don't look at these as like, is it below 0.05? You're trying to see, is 0.05 in the range, like the note says below right here. So with this result being inconclusive, where we aren't able to decide, what does it suggest I should do? Since the results are inconclusive, I should do what right now? More whats? Does it only have us do B? Only has us do B. Since 0.05 is in the range, it says what? We should definitely do this. Change to 5,000. Yep. Should be conclusive. So now, let's take a look at it. More permutations. Basically, it's like a better estimate. More permutations gives a better, stronger estimate. And did I do something wrong? Well, sure. Okay, I broke it. And there. I like the y tilde x comma data equals 5,000. And we do have a seed to replicate our randomness. And now, why is my test conclusive? Is it running? It is running. Good. Is my test conclusive? Well, first off, we have to know if it is conclusive. Is my test conclusive? Explain to me. This test is conclusive because your interval now is completely what? Or you could say this is not in it at all. So my test right there is completely conclusive. And you also notice it's a smaller interval. The second test is still inconclusive. We're looking at only the mean test, the test of the means, which is conclusive. This one, if we were to look at it, is not conclusive because of that, like yes and no. And this one is conclusive right down here because no and no. So like you'd be asking, is this statistically significant? Is it statistically significant? And this one is conclusive because 0.05 is not in the range. So conclusive is when we do not include 0.05 in the range to estimate what the p-value might be. Is this statistically significant? Yes. Is this statistically significant? Yes. Is this statistically significant? No. Is this test conclusive? Yes. Is this test conclusive? No. Is this test conclusive? Yes. How, John, does this make sense right here? To tell if a test is statistically significant, look at the p-value. To tell if a test is statistically or conclusive on that result, look at the interval to see if 0.05 is in the range, and which is this is really covering. And if 0.05 is in the range, increase the permutations to get a better estimate, which that's what we're doing with the permutation procedure is we're estimating the p-value. How's that look, John? This is about the conclusivity of p-value intervals. And make sure you remember this is just p-value intervals. This is not all intervals because some intervals are used to estimate other things. We're just trying to estimate the true p-value. So this is not a p-value. It's actually an estimated p-value. And then we think it could be between these values. Let me know if you have any questions. I think that's got it. John, I just want to throw you another 100 points. Thank you, John, so much. Excellent work. If you have more questions, let me know. We're going to upload to more 201. Let's do this. Okay. Let's take a look. 201 time. Time for those chapter 5 areas under the curve. People might think I'm crazy, but they are my absolute favorite questions. I like to guess them. I can usually get them right. Take a look right here. Here we go. Chapter 5. Homework, part 2. We'll talk about some tricks for this. Here we go. I believe I found the right one, Summer. So tell me, Summer, if this is the wrong one. We'll work on it here in a moment. Take the timestamp on it. Well, let's go check it out. Chapter 5, part 2, areas under the normal curve. Let's do this. So whenever we get to this problem right here, we want to have open the David M. Lane applet. It's going to make our life really easy, really quickly. So you'll see the link in the chat right here in a second, and we will use this applet to solve the questions. Now, when you're doing the test, you won't have the applet, but you could have pictures. Check out some of our videos or the end of class where we work on example problems, coming up with our own example test questions. I wanted to see the example test question. There we go. So we do some example test questions. Canvas content are great examples, but we did this example earlier, and it's just like a Canvas content. Check out earlier office hours today for that, see what tests might look like. But you can also work problems with the David M. Lane, which is the link Mubot just put in the chat. So let's get both of these situated on the screen right here. 2 seconds. We'll put the problems on the screen at the same time, and we almost have the screen oriented. I might actually have to disappear. Maybe not. There we go. Nice and neat. Here we are with the applet on the screen and also the pictures on the screen. So what we want to do, and we always like to take one guess at it. First off, the z-scores on the applet go from -3 to +3 from this side to this side. The normal curve usually graphs 3 standard deviations below the mean, 3 standard deviations above the mean, and this is what's called the standard normal because we use z-scores on it. You could do context, like if you talked about a test with a mean of 70, if I knew how to spell. 70 is a standard deviation of 10, and you can see a mean of 70, standard deviations of 10 going up. We usually do standard normal every time we do it, at least put that below it so we can see the z-scores. This over there is a standard normal curve. Everything on it is z-scores. So we want a z-score of 0.9. Well, 0.9 would have to be on the right side, and you'll notice it says greater than 0.9. So that would be right here on the right side and above it. I do like to take a guess at this though, and I'll tell you why. It helps us understand how to work with the curve. Because when you think about this, you could just put in right here 0.9 and we'll see the answer. We'll do that in a moment because we want the area above this. Look at how the graphic looks. The graphic I make over here should look just like it. But I will throw a big 200 points. If anyone knows in the chat, what area is above 1 on the normal curve? Someone's probably watching the video later and he's like, oh, I know it. The area above 1 is what? The area above 1 is how much percent of the curve? The area above 1, there we go right there, is how much percent of the curve? Oh my gosh, the curve is crazier here. This is what we drew out during class for practice. Above, and we even got it highlighted almost, the area above 1 is what percent of the curve? 68 in the middle. And then above 1, if you have 32% outside, above 1 is only 16%. That's not where 1 is at. We drew a whole bunch of different curves, but above it is 16% according to the empirical rule. So we're not quite at 1. Oh, Summer, 200 points. You got it, Summer. Great job right there. So Summer, and check this out. If we're here at 1, it'd be 16% above it, but we're a little to the left of it. So I'm thinking it's a little bit more than 16, like 19.32. I see this one's too hard to guess. So now let's find the actual answer. We were close. The actual answer is this. Those were my guesses, but I guessed about 19% and it's 18%. Does that make sense? Your graphic should match this right here. Does that make sense, Summer? this graphic right here will look like this graphic right here, and then the percentage will be this number here. That will be the right answer. So now we're just doing the same thing, but it says the area below a z-score of 1.15. So let's continue on. Now we're at 1.15 and graphing below. Summer, what do you think? A, B, C, or D? If we go to 1.15 and graph below it. So do you think that's A, B, C, or D? If we go to 1.15 right here is z-score. So the z-score of 1.15 would be right here, and then we graph the area below that. Would that be A, B, or C, D? Which one? You go to one. It'd be A. Great job, Summer. There, another 100 points. Excellent work. So I always like to take the guess, remember? So if we were to say, and watch this, if we were at 1, there's about 16% above, but we're a little bit over here. This is now a decent test question. How would you find the area below? We know the area above. So Summer, what would you do right here with this area? Like if you were presented this on the test, and we can easily just click this button right here and find the answer. I'll show how to find it to double check your work. But if you want to find this area over here on the curve, and you have this area over here, what would you do mathematically? Subtract it from what? This is just like kind of getting us ready for what a test could look like. We could have this image on a test, and then we could have to find the other side of it. So if we want to find the other side of the curve, we know this is about 13.57%. How could we find the other side of it? And then we'll use the calculator to get the real answer, which we will have. So we know this area. We want this area. Hint, they add up to the full curve. Exactly, subtract from 1 or 100%. And there we go right there. And here's how we check our work. You are correct. It's just the other side of the curve. Summer, great job right there. And let's say below. And you want to make sure your graphic matches. Look at the graphic right here and make sure it matches. And then look at your work. Be like, this is below 1. Oh my gosh. Look at that. We almost made an error. So you would subtract from 1. Just make sure to not forget a decimal. These are complements. So don't forget. I almost forgot a decimal. And that would have been wrong. So we almost got one wrong today. We'll get others wrong, I promise. So now this one looks a little bit confusing. But this is the area between. This one really doesn't work for many test questions. Which of these, A, B, C, or D, looks to show an area between? Does A, B, C, or D look to show an area between? So this one right here, and just notice how this is button 3, and it's question 3. Hint, hint, hint. You can probably guess where button 4 is going to be used for. So this is question 3, and on the app, it's button 3. And which of these shows an area between two numbers, which says a z-score that is contained in the interval negative 0.75 to 1.4. So which of these shows the kind of between idea right here? The between idea, is that A, B, C, or D? Which of these would be the between idea? I would say the one that is showing an area contained between two numbers, like the shaded area. It is C. Great job there again. Summer getting all the points today. Love it. So we're going to go right here and put negative 0.75 to 1.4, and then we ask, does our graphic look like that? And the answer is yes. And we're just going to take that answer right there and get the answer correct. Make sure your graphic, whatever you draw here, looks like the answer over here, and then you've done it correctly. Like have it split screen like I have if you want, but your graphic should over here look like the graphic right there. And then the last one seems a bit odd because the last one is saying a z-score greater in absolute value than 0.5. So that means something like negative 0.6 would be greater or positive 0.6. It has to be greater in absolute value. So this is an outside idea. So which of these looks like an outside? A, B, C, or D? As though we went to 0.5 and said the absolute value of it has to be greater than 0.5, like negative 2 or positive 2. Well, we need to shade in those areas. It has to be greater than the absolute value or in its absolute value greater than 0.5. And which one of those would we be at again? Let's see. For this one, greater than absolute value, we're doing the outside, and that would be graphic. And excellent work. And then I'll plug in the numbers here. You got it again, Summer. Excellent work. It is C. And the answer is 61 point this right here. Summer, do you have additional questions? We have time for a little bit more. That's got it. That's a really good one right there. That is a tough problem, Summer. Like just understanding what you're seeing with the graphics, understanding like what it's showing you. Good problem right there. Are there any other problems you're wondering about? Let me know. Let's hop back to the main screen. Yeah, let's do the downhill skiing. Good questions. Probably. Let's do the downhill skiing one. Awesome. 506. You're welcome. Anytime. Thank you for swinging by. Sometimes on like Thursday, I think everyone's like, I'm sleeping. It's Friday. It's not Friday yet. Downhill skiing. This one we actually put on a test, and everyone's like, did we ever do this problem? I'm like, it was on the homework. We like almost copied it verbatim for a test one semester. You're saying, please do that again. We might. You never know. Here we go. Downhill skiing. Let's check it out. Okay, so we have the mean time was 103.12 and the standard deviation was 2.88. If the normal model is appropriate, what percent of times would be less than this? Now, here's the trick to this, Summer. You ready? This value over here is always on a z-score. So think about this. If we have this data, and here's the mean, that's the symbol for the mean, here's the standard deviation. What is the z-score of this? All I'm asking is, how many standard deviations above the mean is that value? The mean is basically, for all intents and purposes, 103, and the standard deviation is 3, and that value is 106. So that is a z-score of what? What is the z-score for that? So that is a z-score of basically, and yours might be negative or positive or 2 or 3, but mine is a z-score of what? It'll always fall on a whole number. Mine is a z-score of what? So at the center of the curve, I rounded the numbers, but it'll work if you round them because it's always a whole number. I wouldn't suggest solving all problems like this, but this works on the downhill skiing. It's 1. Great job. So what number? Great job, Summer, right there. More points. What number do you hear in your head as the first number of the empirical rule if I do the following? The first number on the empirical rule is what? And I'll explain why we're doing this here in a second, but the empirical rule is going to help us out. Between -1 and 1 is what percent of the data? We need to know the 95, 99.7. Earlier today, good question there, John. Today's morning office hours, the timestamps are 5 minutes in and 12 minutes in. The morning office hours this morning. And John, let me know if you can't find them. I will link you in the video. I can do that here right after this. You bet, John. So 68, that is correct. So now the reason we're doing this is it wants to know the percent of times less than this. You're welcome, John. Here's the easy way of doing this. If 68 is inside, what is total outside? So we always do what's called the inside-outside trick. So we say 68% inside, this outside, and then we cut it by either hand by cutting it in half. So 68 inside, then what is total outside? And then you could go to the next step of cutting it in half. This is one of the harder parts of the problem, I'd say. Like this is one of the, usually this problem part is missed, but this is empirical rule stuff right here. Using 68 in the middle, then you say this outside and then cut that in half. This is where you get like really quick and good at it to be like, okay, I got this. You go 68 inside. So what would we say? You can solve the whole thing or tell me the sides and then I'll solve the rest of it. So what would we say right here? You, Summer, 100 points again. That's it. Now here's where usually a mistake is made. Yours might say above or below. The easiest way to do this, Summer, I think, might be to subtract from 100. I'll just kind of say this right here. If you subtract from 100, the amount below is 84. You can also add up those amounts. But the amount below is 84. The amount above is 16. So that's what we would have right there. The amount below is 84. The amount above is 16. Also, our pictures that we drew in class can be a huge help too. So that is the amount below, 84%. And we should get it right. Cross your fingers. Is it below? Less than, correct. Now that's according to the empirical rule. But let's not use the empirical rule. Let's use the data. There are 53 ski times as it says. We are asking about the time of 106. That would be right here. If there are 5 above, how many ski times would be below? If there are 5 ski times above, how many ski times would be below out of the 53? There's 5 above, so how many would be below? If there's 5 above, I hope I spoke properly. Out of the 53, if there's 5 above, so if there's 5 above it, which we've shown right there visually, the amount below, which I should have done this way, I should have highlighted those in red like this. The amount below. So there's only 48. Got it, Summer. Yep. Much easier than counting them up. Yeah, I gotta make a little party. So this is the actual, like, how many are actually below, not what the normal model suggests. So 90.6. A little bit different. Okay. This is where I get scared. This question always works out the same way. Every time you solve it, this will always be the answer. So if you're watching the video, if I get it right, you get it right. I'm not second guessing myself too much. So I've done this one a lot. Those answers are a bit different. Like if I tell you I'll drive you 86% of the way to New York and I drive you 90% or 84 to 90%, that's a bit of a difference. It's a bit of a difference in like percentage complete. So I would say no, these percentages do not agree because the normal model is not appropriate. So the normal probability plot shows that the normal model is not appropriate. So there's only 2 possible answers. Begone bot. So yes, because the normal probability plot is appropriate, or no, because the normal probability, or no, because the normal model is not appropriate. So I'm going to say they do not match because the normal model is not appropriate. Woohoo! If they matched and were closer, it would be appropriate. Now here's the thing, we need to find the histogram of it. Notice that the highest time is 113. That automatically tells us what the answer is. With the highest time being 113 and 109, the answer must be what? This tells the answer instantaneously. It says, what do you think, Summer? The highest time was 113. Which of these looks to basically show a histogram where the highest time was close to 113? So this will narrow down the option by looking at this alone. And we can look at the data and be like, okay, the highest time was 113. What do you think? It's A. Yep. So that narrows it down pretty quickly on that by identifying that right there. What can be seen in the histogram? The histogram is going to show a little bit of a right skew. There's our Monster Man. We always got to draw the Monster Man. We miss you, Monster Man. We don't talk about Monster Man nearly enough. He's a little bit right skew, He's missing his tooth today. There we go. He's a little bit right skew, tiny bit of right skew with some outliers maybe. So there's a little bit of right skew right there, right to the high, left to the low, whatever way that Monster Man's tail goes. Little bit of a right skew. He's pulled out a little bit to the right side right there. And that's got it. This one right here is a pretty good one. Says fewer than 2, 2.5. That means we would be this much below right here, which is impossible. There we go. These data are strongly... That's a ridiculous skew to the right. There we go. Yay! Could we finish the quiz? I mean, the homework? Oh, we could... I don't know. Hey, Aaron, can you help me with question 3 on chapter 4 quiz? Yeah, Bryce, great to see you here. We got just enough time. Let's take a look at it. Let's go head back to the main screen. Let's do this. Okay, Bryce. Chapter 3... Question 3, chapter 4 quiz. Which, Bryce, can you tell me what the question is? Because when you take the quizzes, it'll always change what the question is. So how does that question start, Bryce? Thank you for being here. So drop the question in the chat. Say, it starts like this. Let me go grab my Pearson. And tell me the start of the question. And with the start of the question, we'll find it. You're welcome, Summer. Excellent work. Summer, thank you so much. It just takes practice. Just show me to office hours, be like, hey, Brian, can work the problem. Slow or fast office hours, you never know. Sometimes, I think Monday, Tuesday, Wednesday are like the big days. Horse race speed, the O-give problem. Time for some horse race speeds. I almost found it immediately. I did like another one. We have it. Let's go talk about the horse race speeds with the Ogivs. Stat 201, Chapter 4, Quiz, Horse Races. Let's go check it out. Here we go. Thank you so much, Bryce, for being here. Let's add you as a moderator. And here we are. Now, an Ogiv is a weird graphic. We'll deal with it. Let's click on it and start to think about what it's telling us. These are the percentages on the normal curve, or not on the normal curve, on the data. These are the winning speeds. So let's zoom in on it and try to draw something out. Now, we are going to do our own drawing to answer the questions. And let's think about this. What is probably one of the most important percentages to talk about, Bryce? Hey, Alexander, great to see you here. Oh, man, Alexander, 320 coming up, right? What is one of the most important percentages to talk about, like a percentile? There's a lot. You could pick one. What is a very important percentile to talk about? I'm thinking more of a central percentile, like towards the center of the distribution. What might be a very important percentile to talk about in this data set? Noah, good to see you here too. We got everyone here. Throw some 100 points out. What's a good percent? The 85th? Well, that's the one that's visualized. Good answer right there. That's the one that's visualized. That one, worth some points. How about this one? Let's go over here and talk about the 50th percentile. Now, the 50th percentile is also known as the what? The 50th percentile is also known as the what value in the data set. The 50th percentile is called the what. Like if I say this is where the 50th percentile of the data is at, that is what I would call the what value in the data set. Like, or the what value in the data set. The median, great job, Noah, right there. Excellent work, everybody, practicing the median. Now, this is where you got to zoom in a little bit, so get your zoom ready. The median is just a little bit below where? It's just a little bit below where? Give me a guesstimate of this median. It's a little bit below where? It's about there. We're zoomed in. We're enhancing. My God, it's Jason Bourne. He's in here somewhere. It's where? Where's the median at? Close. A little bit below 36, right? Noah, great job. I think I said it's a little bit below this, right? So 35. I think it's 35.9. I think it'll give it to you if you put 35.8. I think 35.9 because 35.8 might be there. Yeah, it's close. It could be 35.8. I think it has a plus or minus 0.1 on it. So Noah, I bet you would have got it right there. More points, Noah. Great job. So 35.9. I think. Maybe I'll be wrong. Never know. Now another good value to know would be what? I'll give you some hints right here. How about we maybe mention this? Ooh, that one's nice and easy. We got a good one there. And how about we mention, oh, we got lucky again. That's how in the world we get lucky twice right there. What am I pointing to with those blue things right there? '25th percentile. Great job. And can you identify that as Q1? Because if we have 25% of the data, we're at the first quarter. And if we have 75% of the data, 3 quarters. I need to go back to learn my quarters. Q1 and Q3, bingo. Oh, we can maybe talk about some distances right here in a second, right? So Q1 is, I think, the easier one to estimate. It's right there on that. So Q1 is right on what? It's right there. It's perfect. Q1 is what? Q1 is exactly this. Thank you, my Pearson. 34. Makes my day to see that. 34. Nice and easy. Great numbers. Good stuff right there. And then we go here and we get one of the weirder ones again, but that's all right. I'm not blocking that. We get one of the ones up top, but it is on one of those lines, but it's in between 36 and 37. And that would be 36.5. Hey, Daniel, what's up? Awesome. Saw you last night. Everything 100 points. Daniel right there. Gosh, everyone's showing up. I love it. I always like seeing students around. What is this distance, right? Oh, we need a different color for it. This distance right here is known as the what? That distance right there should be what? That distance of 2.5, which we can mathematically see, this distance of 2.5 distance, which is still this distance right here, is known as the what? Because it's the 25th to the 75th percentile. That distance of 2.5 is what? What would we call that? That's the range of the interquartiles. So the range of the middle 50%, that's simply known as what in abbreviation? Because it's like you have 50 cents between here. So that's where the range of the middle 50% is. It goes from that to that. So between the 25th to 75th percentile, we call this the what value. The box itself, the distance the box is across, is known as the what? The IQR. The interquartile range. So it's just the distance. Just think of it as a distance. It's how far are those numbers apart. So that's just a distance those numbers are apart, and that is the IQR, Q3 minus Q1, just the distance. Just think of it as a range. The last two things we should find are the whats of this box plot. The last two things we should find are the whats. The last two things we should find are the what. That's an easy one. Ooh, is that gonna be? I don't know. We'll find out today. That is the what? The minimum. And the minimum is 30.5. I'm going to block it. That doesn't look pretty. Oh, we do have a green. I was using green highlighter. Hold on. So the min. What does a box plot display for us? A box plot displays the what? What are these 5 things right here called? A box plot displays for us the what? A box plot is a visualization of the what? A box plot is a visualization of the what? Who knows? Say in chat. And that's our box plot. I think we've done it properly because I can do a visual check on this. Let's see. Yeah, it looks like it's good. Yeah, it's not 1.5. There we go. That's not an outlier. I can compute that here in a moment. But visually speaking, this is not 1.5 IQRs below, because that's 1 IQR down, because I literally have an IQR, and it's not more than 1.5. We could also check that mathematically, but this point would not be an outlier down here because it's not more than 1.5. I'm literally grabbing the IQR. This is an IQR distance. Like I drew what the IQR is right here, and then I can go 1, and you can see it's a little more than 1 IQR below. I could also check it out mathematically to show that it's not more than 1.5 IQRs below 34. Good to be back. Can you explain finding the expected cell count for a table? Yes. We might have to with this week's activity. Yeah, Daniel, I think we got just enough time to do that. Let's show that here right after this, Daniel. You bet. We got just enough time to do that. So with this, we've done all the work for this question. I think we've got it good to go. So let's put up our screen right here and let's show what we got. As they said on Rick and Morty one day, show me what you got. And then they tried to destroy our planet. It's not good. Okay. So we've got all the numbers behind us, all the answers we've created. And so we have here the median winning speed was 35.9. The lower quartile is 34. That's Q1. The upper quartile is 36.5. The IQR is, that's the range. We need the range. Range is max minus min. We have the max and the min. So we're just going to do that right there. There's the range. Just the biggest number minus the smallest number is the range. And then the IQR is going to be 2.5, the range of the middle 50%. And create the box plot. If you notice right here, here's our box plot right here. You notice that we have a little bit higher of a median. And so it's going to be this box plot here. And it's pulled a little bit to the left side. The distribution is skewed a little to the left. The typical horse racing speed was 35.9. And the quartiles are at 34 and 36.5. Now, I'll mention why it's a little bit left skew right here. Remember our saying left to the low, right to the high, left to low, whatever way the tail goes. So here's where the 50th percentile is at. And it's actually a little more pulled out in this direction, actually a good bit. So there's more data. There's 50% of the data here, and there's 50% here above and below the median, which is right here. And the lower 50% is more spread out. Did we get one wrong? Woo, get so scared. We're on a streak of getting nothing wrong, and we're going to continue that streak. Let's go check out one more question. Daniel, thank you for asking. We want to find some expected cell counts. So let me put finding the expected cell count. So how do we find expected cell counts? Let me put this in the video right here. BS320. BS320. Finding expected cell counts. Okay, let's go take a look at it. Here we go. Expected cell counts are going to be from contingency tables. And so we need categorical data. And so let's make some categorical data. Is it day? No. Gender. Gender, sure. Gender. I tried multiplying the component number. That should be it. It might have me check. So be careful. I think one of the quiz ones doesn't give you these totals. We're not nice like that. So what we need is the expected, or we need the counts. We're going to find an expected count. So here we are with a problem. And if this problem said, find how many females, find how many females we expect to smoke. So find how many females we expect to smoke. So with this right here, we don't have the totals yet. So let's go here and add in the totals of 93. And that's, please tell me if I get a number wrong, because then I'll get the problem wrong. 87 and have I done, I'm thinking 247. Is this correct? I think that's correct. So expected cell count is expected equals row total times column total over grand total. So if we were talking about expected females to smoke, it's this one. So we go row total times column total over grand total. So circle the numbers you're working with. The row total for the one you're talking about times the column total kind of like matches in on it. Got to add them up. Yep. So what should the answer be? Who's got the answer for the last 100 points of the day? And I need to send out the reminder to class in 10 minutes. Oh my gosh, I'm going to grab a snack real quick too. Let me go grab that. See if you can get the answer in the chat, and then we'll check our work. 3:20, class in 10 minutes. Last class of the week. Oh my gosh, one person's waiting. My gosh. And click here. Okay, one person's waiting. No. I know. Okay, there we go. We'll see. It might be. Let's take a look. 87 times 93 divided by 247. 32.76 or 32.75. Do you do the... Yes. Oh, yes. Oh, yes. Oh, yes. I know some people say, well, like, why would we do the decimals? You always do the decimals. And you see right here, there's the number. Wait. Did we do? Wait. We must have done. Did I do the numbers right? Let me double check my work. 87 times. Ooh, look at, I did something wrong on the addition right here. I did something wrong on the addition. That's how you get, see, Brian can't math. I added wrong. Wow. What happened to my brain right there? So I did the numbers wrong. So I got the numbers wrong. The mathematics should be 87 times 93 over 244. And once again, if you watch this right here, 87 times 93 divided by 244. And that is equal to, if you round it to that right there. We could have it display more digits, but does that make sense, Daniel, right there? So it's row total times column total over grand total. And so we're showing the mathematics on the screen for it right here. But carrier decimals, and then input decimals. Expected counts are decimals. Expected counts 100% do have decimals, and that's got it. Great work. Good practice. Random phone calls. With that, that is the end of office hours. And we'll be back. Let's chill a little music. Go grab a snack. And we'll be back here streaming class in just a moment. Bye for now, everyone. Bye. Class in 7 minutes. You're welcome, Daniel. I'm going to get the timer going while I'm here. How much time till class? 7 minutes and 10 seconds. There we go. Timer going. Bye, everybody.